Hey, this is Mr. J here. Let's talk about similar triangles. In this example here, I've got a lot of information on the page, but let's start out with the triangles themselves. You have a smaller triangle, FLO, is a little bit smaller than the other triangle, the big triangle, HIT. And it looks like, if we look at this right here, it looks like that to go from this corresponding side to that corresponding side right there, it looks like we're going to multiply times 2. All right, to go from that one to that one, looks like we're going to multiply by 2 as well. And to go from 25 to 50, looks like we multiply by 2 as well. So there appears to be a scale factor of equal to 2 if we go from small to big. And then we also appear to have a scale factor of a half if we go from the big to the small. So that's how we can easily figure out the scale factor, is by setting up ratios of the corresponding sides. Okay, looks like that I know that this angle here is 90 degrees and that angle is 90 degrees, and I'm going to explain why. So look at this triangle down here in the lower right. It's a 3, 4, 5 special right triangle. It's a Pythagorean triple, which means that the a squared plus b squared is equal to c squared. Okay, and there's others Pythagorean triples, but this is the smallest Pythagorean triple in terms of the numbers. Okay, well, notice that these triangles up here are nothing more than triangles that looks like that the scale that a factor has been multiplied by these 3, 4s, and 5s. So in this case, it looks like a factor of 5. In this case here, it looks like a factor of 10. Right? 3 times 5 is 15. 3 times 10 is 30, and so forth for the other sides. Okay, so that's how I know that they're a right angle and everything, because they all relate back to this 3, 4, 5 special right triangle, this Pythagorean triple. In a later unit, we're going to learn about trigonometry, and you're going to be able to see that I'm able to tell you that for sure that angle right there is going to be about 37 degrees. And that means that when we subtract 37 from 90 degrees, because these angles are complementary, it looks like we're going to get 63 degrees there. And so it looks like that we have now established our first rule, our properties of similar triangles. And that is that they will always have 3 pairs of congruent corresponding angles. Okay? Congruent corresponding angles, the thing that gives it away. So right up here, look at this right here. This is what we're going to call is the triangle similarity postulate, or what I like to simplify as the rule. And we know that 2 triangles are always going to be similar if they have 2 pairs, at least 2 pairs of corresponding and congruent triangles, corresponding and congruent angles. All right, so that's how we know that angle L is congruent to angle I, and also we could say that angle O is congruent to angle T would be our 2 justifications, our angles that we know that these triangles are going to be similar, because that is a rule that's given, angle similarity. So let's move on to the proportional corresponding sides. So any pair of similar triangles is going to have 3 pairs of proportional corresponding sides. And notice I've set up this 3 ratio or 3 fraction proportion down here at the bottom, setting up the corresponding sides. In this case, I choose to set it up as small over big, so I'm going to come over here and I'm going to start with the small side there, 15, that corresponds to 30, and then I'm going to take the 20, which corresponds to 40, and the 25 that corresponds to 50, and I've set up these 3 fractions. And you'll notice that in all 3 cases, they reduce down to this 1/2 scale factor that I've already talked about up here. Well, the reality is that if you did big over small, you would end up getting that scale factor of 2, because you would just simply find the reciprocal of each one of these. 30 over 50 is 2, 40 over 20 is 2, and 50 over 25 is 2 as well. So that's how we know that these 2 triangles are similar, because they have 3 pairs of proportional corresponding sides. So that information right there would be what we would use to justify that postulate right there that says that if you know that all 3 sides of all 3 corresponding sides of triangles are proportional, then you know that they are similar. All right, we have this last one here, side angle side, and it looks a lot like the side angle side we did in triangle congruency. All right, so we already know that we have these 2 pairs of sides, right? This side and that side, which is here corresponding, and then there and there corresponding, right? And we've got this angle right there in the middle, L and I. We already know that they're congruent, right? We've already set that up here. So if we're able to string together, in this case, let's make sure we get it right, FL over HI right, is equal to, what do we got? LO over IT. And so that's the two pairs of proportional sides, and then we know the angle L is congruent to angle I, which is sandwiched right there in the middle. It's included. Then we know that we have two pairs of corresponding sides that are proportional, and we have this included angle that is known to be congruent. And so that's the third way that we can establish that triangles are similar. So quick review: two properties, two pairs of two properties of similar triangles. It's going to have three pairs of corresponding congruent angles, and it's going to have three pairs of proportional corresponding sides. And we also learned down here that there's a special right triangle that we will learn about in the future, and we've learned that there is a scale factor going from big to small, from small to big, or big to small, that usually will be a reciprocal of one another given the information.